Hi there and welcome to this video for Senior Physics on nuclear physics. In this video we're going to be looking at the variation in binding energy. Now you will have hopefully watched the previous video where we looked at mass defect and binding energy, and we hopefully understood the idea that the binding energy is the glue which basically holds all of the nucleons, that's the neutrons and the protons, together. So we've got this energy which is sticking these nucleons together, and they're going to vary depending on the size of that nucleus. And predominantly the size of the nucleus is directly related to the number of protons and neutrons. So if you take something like hydrogen is going to have a fairly small binding energy because, let's face it, it's only got one proton. There's nothing else really which is holding it in place. But if you take something like uranium-238, you're going to find a massive amount of protons and neutrons all combined together. And that binding energy is basically going to try and hold the whole thing together. Now, we were able to calculate the amount of energy that this binding energy represents from the change in mass from what we had from our stable nucleus to the actual components that made it up. Now we can put all that energy, or we can put all that data together and place it onto a graph. Now the graph will then basically show the atomic mass and the amount of binding energy per atomic mass. Now remember, the atomic mass is made up of those protons and the neutrons, hence the nucleons. So as the mass goes up, we would expect to see a change in the binding energies, and we notice a number of things. So here's a graph that can basically show what I just explained. We've got atomic mass along the bottom, and we've got the average binding energy in mega electron volts up the vertical axis. And what you'll notice is, as we go through the elements, we've got hydrogen way down at the beginning with a binding energy of 1 mega electron volt. Now remember, that's the smallest nucleus that we've got. And then you can see we've got 238 uranium, which is sitting high up round about between that 7 and 8 mega electron volts. Now what we'll find is that as it curves, as it changes, as the number of nucleons and protons increase, we get this increase in binding energy up to a specific point. And at that specific point, we say that the nucleus is then stable. So iron basically at this point here, so iron Fe56, basically has a binding energy which is so big, the result is you can't put any more energy. It's the most stable point of that nucleus, because you'd have to put in a lot of energy in order to break it out. But you can see from iron onwards, going down through strontium, barium, and finally getting into uranium, we get the idea that the binding energy begins to decrease, and this is why uranium begins to split up. It doesn't require, or its binding energy is quite small compared to the size of the nucleus, and this is where this instability comes from. This instability, as a result, will cause these radioactive particles, or these nucleons, to break down, this nucleus to split up, and the result is that we will get new elements which are going to be created. So we've got this most stable point at iron 56. Anything which is heavier than iron 56 basically will undergo fission, and that means it's going to break into smaller particles which will make obviously new elements. So we may get so basically the nucleus will split into two, and the combination of the number of protons and the number of neutrons will make up those new elements. And obviously we can then start talking about, well, what is their mass like in relation to the original mass, and if there's a discrepancy between two sides, that's going to come off in the form of energy. Basically what we've done there is split the atom, and that is the fundamental concept behind nuclear power. So anything with a heavy nucleus will basically undergo fission, and likewise on the other side, anything which is too small is likely to actually fuse together. So something which is smaller than that stable iron has the ability to fuse with other nuclei, and the result is we get nuclear fusion. Now, nuclear fusion is a lot cleaner than nuclear fission, and that's obviously something that we will look at later on. So what you need to be able to do is be able to interpret what how this graph works, and then basically take information off it. Okay, well, I hope that makes sense, and I hope you sort of understand that every element is going to have its own specific binding energy, and that binding energy is directly related to the number of nucleons that it's got held in its nucleus. Okay, well, thank you for joining me, and I look forward to you meeting again soon. Bye for now.